All right, so last time we saw that the length of my curve is the integral from alpha to beta, square root of dx dt squared plus dy dt squared dt. So now we're going to do an example. So find the length of the curve so find the length of circle when, so we're going to do part A, so we're going to do x is equal to cosine of t, y is equal to sine of t. So t is between 0 and 2 pi here. So I misspelled circle pretty badly, so let's fix that. So what we're trying to find here is we're trying to find the length of this circle, and that's just the circumference. This is a circle of radius 1, so we just expect this thing to end up being 2 pi. But we're going to go through and do this. So the length then, so let's figure out my derivatives first. That's probably a better idea. So I'm going to have dx dt, it's going to be minus sine of t. dy dt is going to be cosine of t. And my length then is going to be the integral from a to b, so t goes from 0 to 2 pi, of the square root of dx dt squared. So I'm going to get negative sine of t squared plus cosine of t squared dt. This is the integral from 0 to 2 pi of the square root of sine squared of t plus cosine squared of t dt. This is the integral from 0 to 2 pi of the square root of sine squared plus cosine squared is 1. So let me shorten that. So this is the square root of 1 dt. This is the integral from 0 to 2 pi dt. So this is t evaluated from 0 to 2 pi. This is 2 pi. And now we're going to do part B. So that was what we were expecting. So now use the parametric equations, and these equations are from the first section. So I showed you guys both of these equations in section 10.1. So we're going to use the equations x is equal to sine of 2t, I believe. Yeah. And y is equal to cosine of 2t. So you'll remember that, when I drew this, what this was a circle. It was still a circle, but I transversed it twice. So now we're going to see that if I try and find the length here, so let's find dx dt, which is 2 cosine 2t, dy dt, which is negative 2 sine 2t. So don't forget to use chain rule, that's where the 2's are coming from. I'm going to have then that the length is the integral from 0 to 2 pi, square root of dx dt squared. So I'm going to have 2 cosine t squared, plus dy dt squared. So I'm going to have negative 2 sine of 2t squared dt. This is the integral from 0 to 2 pi, square root of 4 cosine squared plus 4 sine squared. So I can factor that 4 out. If I pull that 4 out of the square root, it becomes a 2. I'm going to have the square root of cosine squared of t plus sine squared of t. Sorry, these should be 2 t's. Drop the 2's. The only thing that changes is I have to write those back in there. Nothing else about the problem changes. So then pull the 2 out. This becomes the integral from 0 to 2 pi. Square root of 1 in there. This is just 1. So this is 2t evaluated from 0 to 2 pi. This is 4 pi. So you can see what happened here. We didn't transverse the curve once there. We actually transversed it twice. So we're going to move on to the next example because it's the last one. So let's go ahead and jump in. So find the length of one arch of the cycloid x is equal to r theta minus sine theta, y is equal to r times 1 minus cosine theta. And we have 0 is less than or equal to theta, less than or equal to 2 pi. So we found that, in one of the earlier examples. Okay, so let us begin by calculating our derivatives. So we know that we're going to need dx d theta. We're going to need dy d theta. So dx d theta is r times 1 minus cosine theta. dy d theta is r times sine theta. Okay, so now I'm just going to plug this into my integral. So my integral then is the length of this thing is the integral from 0 to 2 pi times square root of dx d theta squared. So I'm going to get r squared 1 minus cosine theta squared plus dy d theta squared. I'm just going to go ahead and plug in r squared sine squared theta d theta. And now we're going to compute this integral. So we're just going to do as much simplification as we can. I have r squared 1 minus 2 cosine theta plus sine squared theta, plus cosine squared theta plus r squared sine squared theta d theta. Keep going, just simplifying. So this is going to be r squared minus 2r squared cosine theta plus r squared cosine squared theta. I don't know why I keep trying to write that as sine there. Plus r squared sine squared theta, d theta. This stuff here, I can factor out an r squared, and that's cosine squared plus sine squared. So that's just going to be an r squared there. So this is the integral from 0 to 2 pi. R squared minus 2r squared cosine theta plus r squared d theta. And again, that r squared comes from the r squared cosine squared plus r squared sine squared. This is the integral from 0 to 2 pi times square root of 2r squared minus 2r squared cosine theta d theta. So what we're going to do now is we are going to pull out the r. So if I pull out the r, it comes out of the square root, loses the square. I'm going to factor out a 2. I'm going to get 1 minus cosine theta d theta. And now we have to evaluate this integral. So this one is one we haven't seen before, but there is a trick to do this. So you'll remember that sine squared x is equal to 1/2 1 minus cosine 2x. So if I take x equal to theta over 2, I'm going to get sine squared of theta over 2 is equal to 1/2 minus 1/2 cosine of theta. Sorry, let me leave that right-hand side alone just because of what I'm trying to solve for. So I'm going to get 1/2 times 1 minus cosine of theta over here. So that tells me that 2 sine squared theta over 2 is equal to 1 minus cosine theta. So I'm going to take that and plug it now into my integral. So this is the integral from 0 to 2 pi, r times the square root of 2 times 1 minus cosine theta is equal to 2 times sine squared theta over 2 d theta. So this is the integral from 0 to 2 pi, r times square root of 4 sine squared theta over 2 d theta. Pull out the 4, it's going to become a 2, so I'm going to get a 2r out here. Integral from 0 to 2 pi, square root of sine squared theta over 2 d theta. I'm just including every step because I don't want to lose anybody along the way. So this is the integral from 0 to 2 pi. Sine squared theta over 2 is positive between 0 and 2 pi. So when I take the square root, I don't have to worry about the absolute value there. Otherwise, I would have to break up the integral over where it was positive and negative. So now I can integrate this is the point. So this is going to be negative cosine theta over 2, and then I'm going to multiply by 2 to get rid of the factor of 1/2 when I take the derivative. And this is going to be evaluated between 0 and 2 pi. So this is going to give me 4r when I pull the 2 out times, let's go ahead and do a minus sign. Bring out the minus 2. This is minus 4r, so then I'm going to have cosine of 2 pi over 2 minus cosine of 0. So just evaluating the integral, I pulled the 2 and the minus sign out. And that's where they've gone. So what I get now is this is minus 4r times negative 1, because this is cosine of pi, which is minus 1, minus cosine of 0, which is 1. This is negative 4r times 2. This is times negative 2. This is positive 8r. And so you can see that with these problems, again, with the square roots, you're going to have to kind of be set up to do these and be able to do these integrals exactly. So, again, if we're trying to save time on the exam, I'm not going to ask you to do these integrals. I'm just going to ask you to set them up because most of the time you're not going to be able to compute them exactly anyway. But anyway, so that's kind of an interesting example. So I'm going to stop here. That is the end of this section. I plan on hopefully this week doing, getting some problem solving videos out where I just go through a couple homework problems that I think are a little more challenging. I'm trying to get your guys' exams graded. I plan to have those finished, but it's going to take some time. Hopefully by Wednesday night I'll have them finished. So don't expect any videos or anything like that until after that. But I'm going to upload all these tonight. So I'm going to stop this video here. If you have questions, again, feel free to leave comments. I will try and answer them. So yeah.